Good morning everyone. So in today's session in high-speed aerodynamics, we are going to discuss about the momentum equation. So last class we discussed about the continuity equation, right, which is nothing but the conservation of the mass. So today's equation which we are going to discuss, that is momentum equation. This is nothing but the conservation of momentum, right? So what is momentum equation? So the basic principle of momentum equation is that time rate of change of momentum of a body equals to the net force exerted on it. So if you are writing in that a vector form, what we are telling, time rate of change of momentum, that is equal to the force exerted on the body. So if we are taking the mass as constant, so what we can write this particular formula as m into d by dt into v equal to f. So what we know, dv by dt, that is velocity with respect to time, we will be calling it as an acceleration, right? So f equal to m into a. So f equal to m into a is nothing but what it is, Newton's second law, right? So this momentum equation tells us the Newton's second law of motion, right? So that is nothing but force equal to mass into acceleration. Now consider that what are the forces which is acting on a controlled volume. So now if you are taking a control volume, what all forces will be acting? So from basically what we can tell like body forces acting on the fluid inside volume V and surface forces acting on the boundary of a control volume. So on the boundary of a control volume, what are the surface forces? So one is body forces which are acting on it, another one is the surface forces which are acting on the boundary of the control volume. So first we will be discussing about these two forces, how it will be dealing. So because what we are telling, F equal to m into a, right, that is the force equal to mass into acceleration, and so this is nothing but force equal to change in moment, right? So change in moment, what we are writing, f into v into d by dt. So if it is mass is constant, m equal to dv, m into dv by dt is coming, right? So now we will see what are the forces which are acting on the fluid element. So now what is the main one? First one is the body forces, another one is the surface forces acting on the boundary of a control volume. So let's come to the body forces acting on the fluid inside. So now the force, these forces whatever is there, so it will be action at a distance, that is nothing but we will be having the gravitational forces and we will be having electromagnetic forces exerted on the electromagnetic forces that may exert on the fluid inside volume V. If we are taking a control volume, so inside that, in the on that control volume, so on that one we will be having a gravitational forces and electromagnetic forces which will be acting on that, right? So these two will be acting on the fluid inside, so due to force fields acting through the surface. So now what we are taking, let F represent the body force per unit mass of a fluid. So if we are taking it as a body force per unit mass of fluid, right? So now what we will be taking, we will be considering a control elemental volume dV. So we will be considering elemental volume dV. So dV is nothing but elemental volume. So inside V, the elemental body force on dV is equal to the product of mass. So what it is, elemental body force on dV. So that is equal to product of mass and the force per unit mass. So now what is mass? Density into volume, right? So we can write what we are taking, elemental volume we are taking. So in place of product of mass, in place of mass we are writing rho into dV, and what we are telling, we are telling force per unit mass. So into F we will be taking. So if you are considering the overall total body force, then what we can write? So it is like total body force if you are taking for a control volume, right? So volume integral we will be getting. So volume integral of, so product of, that is rho into dV, mass into force which is acting. So further about how we can write this one as a volume integral of rho F dV we can write. So this is the body force which is acting on the fluid inside, right? So inside fluid element what we are having with one of the two forces which is acting is, one is like body force we are telling, another one is a surface force we are telling, right? So on the body force, what it is like action at a certain distance which we are occurring, that we will be calling it as a body force. So on that body force we have the gravitational and electromagnetic forces will be exerted on the fluid inside due to force field acting through the space. So now what we are considering? We are considering a F represent body force per unit mass of the fluid. We are considering a elemental volume del V inside a V of a V. Inside the V, the elemental body force on del V what we are considering, that is equal to the product of mass and force. So M into F. So this particular M we are writing in terms of rho into dV into F. So this is for a single element. If we are taking the entire complete control volume, means at that particular time we will be getting in terms of the volume integral, right? When you are considering for the entire body. So coming to the surface forces acting on a body of the control, boundary of the control volume. So again these surface forces in a fluid stem from two sources. So what are that? One is due to pressure, another one is due to the shear stress distribution over the surface. So now what we are dealing with the inviscid flow. So when we are considering the inviscid flow, we will not having a shear stress term. So only we will be having the surface pressure, surface forces due to only pressure. We don't have the effect of a shear stress since we are considering the fluid as an inviscid flow, right? So now what we will be taking? We will be considering a control volume. So inside a control volume, we are considering a elemental area ds. So this is this elemental area ds we are considering. Okay. So the elemental surface force acting on the surface area is given as minus PdS. Okay. So why this particular negative sign has come is because the pressure what is acting on the body, it is on inside. Inward it is acting. So opposite to the outward direction, that vector direction which we will be having in outward direction, but the pressure is acting inward. So that's why negative P has been come. So hence the summing of the complete surface. So since this is for the single elemental force surface only, right? If you are taking the total surface force due to pressure, if you are considering, means what we will be having, this one we are dealing on the surface. That's why we will be getting the surface integral of minus of P ds. So we can write this as surface integral of P ds, right? So what type of two forces which we have seen? One is a body forces acting on the body, another one is a surface forces acting on the boundary of a control volume, right? So in that generally on surface forces we will be having two types will be there. So one is pressure and shear stress will be there. So but we are dealing with inviscid flow, so we don't have a shear stress distribution will not be there, only due to pressure only surface forces will be considering. So what is that elemental surface force which is acting? That is nothing but minus PdS. So if you are taking the entire complete control surface, we will be having a surface integral of PdS with negative sign because the pressure is acting inward direction, right? So now if you are taking the overall sum, what we will be having, that is a forces, total force acting will be of what we have. First is body force, that is control volume, rho into dV into F. So mass into force which is active, force per unit mass. Then another surface force is what? Plus of surface integral of PdS. So surface force. So this one we can writing it as a volume integral of rho F dV minus of surface integral of PdS. So this is the total force acting on a control volume, right? So now what we have actually, we have an equation that F equal to force equal to m into dv by dt. So that is nothing but m into a we have written, right? So now we have deal with the what are the forces acting. So now what we have to see the other side what it is there. So if you are considering like previously it is there m into dv by dt equal to f. So that is nothing but ma we have written. So if now we see left hand side, considering the left hand side from the equation 1. So what we are having in our fluid dynamic model, what is there at? Time rate of change of momentum, that is nothing but m into dv by dt with constant mass, how we will be explaining. So what we will be having, so to again by understanding physical intuition, so we will be looking to the control volume. So what it is their control volume? It is fixed in space, right? So it is fixed in that mass flows into the control volume from the left hand side and leaves to the control volume from the right hand side. So mass is flowing inside and leaving from the control volume towards the right side. So when you consider that one, so the mass flowing in brings with a certain moment. So when you are telling there is a mass flow inside and coming outside, right? So when it is going inside a control volume, we will be having with a certain momentum, mass flow will be flowing will be there. So at the same time, when the mass is coming outside the control volume with a certain momentum, it will be coming outside. So by keeping this one, what we will be seeing, so we will represent A1 is the net rate of flow of a momentum across the surface S. So the elemental mass flow is nothing but rho v ds across the ds if we are taking. So ds control volume if we are taking small dl elemental surface if you are taken means, so for that elemental mass flow across ds is nothing but rho v ds. So with this elemental mass flow associated, a momentum flow will be nothing but rho v ds into v. So this is the, so density mass into what? Momentum we will be having, right? Velocity. So from this one, figure that when the direction of v is away from the control volume, this physically represent an outflow of a momentum, mathematically represent a positive value of v ds will be there. So conversely, when the direction of v is towards the control volume, what we will be having physically, it will be representing the inflow of momentum, and mathematically it will gives the negative. So if it is like this velocity is going inside means towards, right? So physically it is like going inside the volume, but mathematically when we are representing, we will be representing it as a negative of VDS. So when it is going towards the outward direction, it is going outside, but mathematically representation here it will be of the positive VDS will be there. So now the net rate of the mass flow entirely if you have taken, so momentum, so net rate of flow of momentum if you have taken, that one what we are telling, so generally it is rho VDS into V we are taken, right? So this is momentum flow, right? So now if we are considering for the overall surface, then what we will be having? Surface integral. So it depending on what we are telling, inward or outward, then the sign by convention will be changed. So if our control volume, even that figure which we have seen, if it is withdrawn in such a way that unsteady flow is there, so then the momentum of the fluid inside the control volume will be fluctuating with time simply due to time variations in the density and velocity. So what we are telling, so if we are taken a control volume for the, if this particular control volume with element ds, so if it is in unsteady flow is there, if it is drawn in such an unsteady flow is there, means then the momentum of the fluid inside the control volume, what it will be having inside the control volume, whatever the fluid is there, it will start fluctuating, right? So thus due to time variation in density and velocity. So therefore, A1 will not be represent the entire contribution of what it is, time rate of change of moment, right? So dV by dt term entirely will not represented by the A1 itself. So what we have to consider? We have to consider the time rate of change of momentum due to unsteady or transient effects in the flow of fluid inside a volume V. So apart from A1 which we have done, we have to consider the effect of unsteadiness of the flow. So now that particular one we will be representing it as a A2 So this representation fluctuation in momentum, right? So we will be considering the elemental mass of a fluid is rho d. So hence this mass has a momentum of rho dv into v, which we will be having. So now that complete control volume, total mass inside a volume is nothing but what is, since it is inside a volume. Okay, inside a control volume means we will be having the volume integral of rho into v into control volume element. So hence the change in momentum in v due to unsteady fluctuation in the local flow properties, what we can write. So this is like only the total momentum inside. So if you want to represent in the change in moment means what it is. So dou by dou t, right? So dou by dou t of volume integral of rho v dv. So this one again we can write as volume integral of dou by dou t of rho v into d. So this is the A2. So now what we have? We have the one term which is where there is no unsteadiness in a flow. We got the rate of change of momentum. Right. So next one, we are finding out due to fluctuation or unsteadiness effect, we are seeing that we are finding out what is the momentum, change in momentum. Right. So that is nothing but this. So by combining these two, where we will be having the total instantaneous time rate of change of momentum of the fluid as it flows through the control volume. So then we will be having a d by dt of mv, which is there in the equation 1 starting. We will be having both time rate of change of momentum and we will be having due to the fluctuations also. So it represents the overall total instantaneous time rate of change of momentum of the fluid as it flows through the control wall. So that is integral of surface integral of rho v ds into v plus volume integral of dou by rho v by dou t into d. So this is nothing but change in rate of change in momentum. Right. So this one which we got the equation for the right hand side. So therefore, it represents, to repeat the physical principle stated that time rate of change of momentum of the fluid that is flows through the control volume at any instant is equal to the net force exerted on the fluid inside the control volume. That is nothing but d by dt of mv equal to the net force exerted. So inside this particular force, what we have seen? We have seen the body force and surface forces acting, right? So here we have seen the represented A1 and A2. So A1 will be the rate of change of momentum which is there. So and this one A2 which we are representing due to unsteadiness, due to fluctuations inside a flow, right? Where a fluid inside the control volume which we are taking. So these two will be giving us the physical principle, that is of the physical principle of momentum equation, right? So in other words, directly what we can write here. So this is nothing but dmv by dt equation equal to f. So what we are having here? Surface integral of rho v ds into v. So where we are considering for the surface only. Then volume integral where inside a fluid element if you are having any fluctuations, right? So how it will be changed. So that is equal to again body force. So control volume we will be having. So volume integral of rho f dv. So that there is nothing but mass into product of mass into force per unit mass, right? So then it will be equal minus of, we will be having a pressure acting on the boundary. That's why we got the surface integral. So PdS. So negative sign is because pressure is acting inward. So again, once again we will be seeing that. So what is equation 1, which we will be having the net flow rate of the mass flow across the surface. Okay, so this one representing the net rate of flow of mass momentum, net rate of flow of momentum across the surface. Yes, we are considering here. So next one, what we are telling. So this one along with this one itself, we will not give the whole contribution for the rate of change of momentum, right? So that is m into dv by dt. So what in addition, what we will be having, due to unsteadiness or the transient effects in the flow inside the volume. So their surface. Now here we are considering, in case inside the control volume, if we are having any unsteadiness or the transient effects are there, means how we will be taking. So we have to take into the consideration this particular one as well. So with that one, what we have the overall equation for this left hand side, that is rate of change of momentum. So we will be having the contribution of on the surface, how it will be varying, and the unsteadiness inside the control volume, fluid unsteadiness inside a control volume, or if any fluctuations are there, how the equation has been come. So with overall, what we are stating, that this physical principle of momentum equation, that rate of change of momentum of a fluid that is flowing through the control volume. So rate of change of a momentum of a fluid. So fluid which is flowing through the control volume at any instant, at any time, that is equal to the net force exerted on the fluid inside the volume. Whatever the force exerted on the fluid inside the volume, we are stating it is equal. So the overall equation, we are having the surface integral of rho v ds into v. So this is on the surface, which is the change in momentum, how it is there, and here we are having, if any fluctuations or unsteadiness are there inside a fluid, inside the control volume fluid. So that is equal to the body forces acting and the surface forces acting on the boundary, right? So this is the entire momentum equation. For suppose, if you are whatever the equation we are having, that is applicable for the inviscid flows, which you have considered, where we told body force, when surface forces are acting, we consider only the pressure forces, because we are dealing with the flows which are inviscid, right? So that's why the equation which is applicable for the integral formulation of Newton's second law apply to the inviscid flow only. So from the equation, what it is telling, that effect of friction, that shear stress terms related it now. See, if in case, if you are including the friction, what it will be additionally, what it will be appear in the surface forces, shear and normal viscous stresses will be integrated over the control. So we will be having the shear and normal viscous stresses will be entire control surfaces we will be integrating. So if F viscous, if we are considering representing as a surface integral, then what we are having the equation of generalized one. So surface integral of rate of change of momentum surface on the surface, then rate of change of momentum inside a fluid where the fluctuations are there inside the control volume, right, for a fluid. That is equal to the body forces and surface pressure on the surface which is acting plus the viscous forces also. So this particular one represents the entire surface integral. F viscous we are considering. So this is the, if we are considering the effect of viscous forces also inside. So the other, or else what we will be considering? So we will be considering, so this particular equation as a momentum equation applicable for inviscid flow. So whereas coming to this equation, since we are adding the Discuss effects also. So this is the momentum equation. So we have taken the reference from the J.D. Anderson author with book name is Modern Compressible Flow with Historical Perspective, 3rd edition. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.